By the end of this episode, you should be able to tell me what is nuclear fission, which isotopes can undergo nuclear fission, and what is a chain reaction.
So from our previous work, we know there's a lot of energy locked up here in the nucleus of atoms. But is there any way we can usefully transfer that energy? The answer to that question is yes, by the process of nuclear fission. What is nuclear fission? Well, any large atomic nuclei with at least 83 protons, such as uranium that we've got here, they have got an unstable nucleus, and they can randomly split into smaller nuclei. So nuclear fission is the process by which unstable nuclei split into smaller nuclei. Now this can happen spontaneously and randomly, but you can also encourage it to happen. So how can we encourage this process to take place? Well, first of all, we need a fissionable isotope, and this is something that can actually be split. And one of the most commonly used fissionable isotopes is the one that we use in nuclear power stations, and it's an isotope of uranium. Okay, now uranium is used as a fuel in nuclear reactors, and it's mainly made up of a non-fissionable isotope of uranium called uranium-238 that we can see there. 92 protons make it uranium. 238 is the number of protons plus the neutrons, and that's an isotope of uranium that we can call uranium-238. But about 2 to 3% of the fuel used in nuclear power stations is not uranium-238, it's actually uranium-235, another isotope of uranium. It's still uranium, it's still got 92 protons, but this is uranium-235, and we can also write that like that. U-235 tells me that's uranium-235, and this is actually what we call enriched uranium. So uranium that contains this uranium-235 is enriched uranium. So we can encourage, or we can induce, the fission of uranium-235 nuclei, but not the uranium-238. That's not nucleable, it's a non-fissionable isotope. But luckily enough for us, uranium-238 is still radioactive, and it will decay into an isotope of plutonium down here, plutonium-239, which is fissionable. So the two isotopes which are fissionable that we can use are uranium-235 and plutonium-239. So now we've got our fissionable nucleus, let's start the fission process. And to do this, we need to give our uranium-235 nucleus that we've got here a little nudge. And we give it this little nudge by firing at it and bombarding it with this low energy, slow moving neutron. Okay, this is actually called a thermal neutron. And what happens is when this thermal neutron hits this nucleus, it makes the nucleus very unstable, and that nucleus then splits into two smaller nuclei. And in the case of our uranium, we can see it's going to split here into two smaller nuclei, firstly barium and secondly krypton. Okay, now if you've got a keen mathematical eye, which I know you probably have, you've noticed something here. Okay, originally we had a mass number of 235. We've got a mass number for barium of 141. We've got a mass number of krypton of 92. If you add 141 and 92 together, it only equals 233. Hang on, this is 235. What's going on here? Well spotted, okay? Because as well as these two smaller nuclei being formed, we also get the release of something else, and that something else is 3 extra neutrons, okay? So we've got our smaller nuclei, our second small nuclei, and the release of 3 more neutrons. If you're a keen mathlete, you've noticed something else, because, hang on, I said this added up to 233 together, 233, 234, 235, 236. We're still not right, okay? But remember, we did add 1 extra neutron at the start here, okay? So we've got the same stuff here that we had at the start. We've just split this into 2 slightly smaller nuclei, and we've released a couple more neutrons there, but we've still got all the same stuff. So just to recap very quickly, our uranium-235 nuclei, we bombard that with a neutron, it makes it more unstable, it splits apart into 2 smaller nuclei and also releases some extra neutrons. So I've shrunk our original image down, and this is basically what we saw in the last slide here with our 3 newly liberated neutrons. So what happens to these newly liberated neutrons now? Well, what they do, these 3 neutrons whiz off, and these fission neutrons, as we call them, remember our first one was called a thermal neutron, these are called fission neutrons, and they whiz off and they hit into other uranium-235 nuclei that we've got here and here, okay? And what is, they cause them to split, and of course when they split, they release 1, 2, 3, 1, 2, 3, they release 3 fission neutrons of their own, which then fly off and bump into more uranium-235 nuclei, and the whole thing happens again. And each time when these 235, these unstable fissionable isotopes, when they split, they release these extra fission neutrons which go off and they bump into more, and the whole thing carries on. And that is what we call a chain reaction. Hence I played the chain reaction song at the start of the video. Okay, so you can see that each one of these fission events sets off 3 more. So you pretty quickly get a lot of fission going on. Okay, you can see that's really going to amplify itself up really quickly. But you know, so what? Why do we actually want to do this? Why do we want to break all these nuclei apart? Well, because each time you split one of these nuclei, you release an awful lot of energy. So there's energy coming out there, there's energy coming out there, there's energy coming out. Every time you split one of these nuclei, energy is being released, and I mean a lot of energy, okay, that's been locked up as nuclear energy, and it's transferred into heat, lots of heat. And we can put that to good use in a nuclear power station by using it to generate our electricity. And just to emphasize here, when I say a lot of energy, I mean millions of times more energy that we'd get from burning the same amount of coal. So if we burn an amount of coal, if we use the same amount of uranium, we're getting millions of times more energy out of the uranium than we would in a normal fossil fuel powered station. And next time we'll look a bit more how that process works.
So that's everything we need to know about nuclear fission and fissionable isotopes. Any problems with that at all, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.